So let's start with our project number 1, which uses Deep Deterministic Policy Gradient, DDPG. And the problem we will be solving is Pendulum 1 or Pendulum version 1, which is a classic control problem. And the objective is teach an agent to string a pendulum up and keep it balanced upright using continuous torque control. So for this, we have in the Deep Deterministic Policy Gradient, we have you can say the components are first is an actor critic architecture, which is separating the doer, which is an actor, from the judge, which is a critic. Then is deterministic policy, unlike PPO, that outputs probabilities. DDPG outputs exact action values, and target networks and soft updates the trick to stabilize training by moving network slowly. And the last is Ornstein Uhlenbeck noise, which is how to force a deterministic agent to explore the environment. So let's import the necessary libraries. Import torch, import torch.in as import torch, optim as optim, import NumPy as np, import gymnasium as gym, import matplotlib plot as PLD and from collection, import TQ for the purpose, and also import the random module. Let's see if it works or not. Meanwhile, we will now import we will now configuration and hyperparameter settings. We will now configure those. First is we'll define the buffer to make tuning easy. We define these things in the beginning to make the tuning easy. Just to run the file again. So first is environment name, which is Pendulum version 1. Another is you can say seed. Then there is device, which is torch.device CUDA. If torch.CUDA is available, else CPU. Then hyperparameters for DDPG, configurations, environment. For the hyperparameters, first of all, we have active learning rate, which let's keep it 1 into 10 to the power minus 4. This is a learning rate for the actor. Keeping it slower is often better. Then we have the critic learning rate. We keep it slightly higher. Learning rate for critic, it learns faster to guide the actor. Then there should be gamma, the discount factor. Values future rewards if it is higher, close to 1, then it values the future rewards. Otherwise, based on the value of it, the future rewards are valued. Then there is tau, which should be 0.005 as we keep it. This is a soft update parameter, like how much of the target net we copy, you can say that. And then is the memory size of the buffer, which let's keep it as 50,000, and size of the replay buffer it is. And then the batch size, let's keep it 64. It's a mini batch size for training. And there is episodes, let's keep it 200 as of now. It's the total training episodes. And there is max steps, in each episode how many steps it should take. Let's keep it 200 also. So max steps per episode. And Pendulum, you can say usually has 200, generally. Yeah. And also let's set the seed for reproducibility. For the torch module and the NumPy module as well as for the random module, let's keep the same seed. Now let's run it. Yeah, it works. It should have worked. Now let's define the replay buffer. In the replay buffer, let's define the whole class replay named as replay buffer. So basically, this stores experience tuples like state, action, reward, and the next state, and done. So like DDPG is an off policy algorithm, which meaning it learns from past data. And random sampling breaks correlations in the data, which basically stabilizes the training. So let's define the constructor. It is using the DQ architecture, the DQ data structure, and the maximum length is the capacity. Then there should be the push, which takes the state, action, record, next state, and done, and pushes it into the buffer. Then you can say we have to sample the batch. So to sample, we define a function over here only. So it basically randomly sample a batch of experiences. Batches random.sample self.buffer batch size. So we get a batch randomly sampled. Now we separate the state, action, reward, next state, done. Basically separate all together, all the arrays together, and now convert all the tensors, convert all to the PyTorch tensors, and move to device, whatever it is, either GPU or CPU. So it returns basically torch.float tensor. It should return them by array of state to device. And similarly for the action, similarly for the reward. But for the reward, we unsqueeze it first. And similarly for the next state and the done parameter also, done argument, done parameter also. Def, we define a length function, which simply returns the self.buffer length, basically buffer length. So this is our replay buffer class. Then now we move on to defining the noise, basically noise process, which is for exploration. So for this, we will define our OU noise, which is basically Ornstein Uhlenbeck noise. Like DDPG is deterministic. Like same state goes to same action. And to discover new strategies, we add time correlated noise to the action. This simulates inertia, which is great for physics tasks basically. Now we define the constructor, which takes the action dimension and mu parameter, theta parameter, which is set to by default as 0.15, then sigma 0.2, and so now we just initialize the parameters. And lastly, we call the reset function to reset the noise. Starting, like basically the state should be static from the initial value. So self.state equals to np.1 self.action dim into self.mu. Initially, every state is kept as mu. For every state, the noise is mu. And a function we will define is sample, where we get the first state as x, and dx is self.theta times self with mu minus x plus sigma value into np dot and randomly selected length, like an integer randomly selected from the state, like the dimension of the state. And so we update the self.state to x plus dx and return it as a sample value. Yeah, so this is the OU noise, and now we will define the neural network. So first one is the actor, which inherits the NN module as a base class. We define the constructor. You can say it as not the output dim, but meaning like the state dim and the action dim, also the max action. So we call the base class constructor first, then initialize the parameters. Not that, but basically the layers. So first fully connected layer is linear dot state dim. It takes the input as state dim and output 400 neurons, and the next one takes 400 and outputs 300. The third one takes 300 and outputs the neuron number of neurons based on that action dim, and we initialize the max action also. Then we have forward, which takes self state, and so let's say dot value self dot fc1, which takes the state, and then the next it is connected to the next layer, which also has the activation function of value, and then we return max action times the dot tan times the fc3a. Yeah, so basically tan puts values in range of from -1 to 1. Then we scale by max action. Example 2.0 torque. So it could be from -2 to +2, the value of the torque. Now we define the critic. It is also similarly inheriting from that class. So one thing is, for the actor, let's document some things as a docstring. So actor takes a state and outputs an action. So it's a simple multi-layer perceptron where the last tan activation is critical here because of the continuous actions, which usually have a range of -1 to 1 or similar. So tan basically forces it to remain in that range. And then now for the critic architecture. So critic takes state and action pair and it outputs a Q value, which is a scalar. So it estimates how good the action was in that state. Like actions, and also note, actions are concatenated into the network at this second layer, you can say. So this is, let's define the architecture. You'll get to know from that. Let's first define the constructor, which takes a state dim, action dim, calls the base class constructor. Now for the initial layers input dimension, it should be state dim plus the actor dim, not the actor but action. And let's define the next unit. The output unit should be 400, then 400 and fc3 should return like just one value output, a single Q value, you can say. Then we have the forward function. It basically concatenates state and action inputs here. And concatenation will be done as, like, we have the activation value. We take the first layer and concatenate the state action on the first axis. Then the second layer is connected to the same Q first layer, and then we connect to it. Then we connect Q to the third layer, which is fc3. So yeah, this is like the neural networks we require. Let's move on to defining the DDPG agent now, like in that class. So let's define the constructor. It takes the state dimension, action dimension, and the max action. it defines the actor first, which takes the state dimension, action dimension, or and maximum action, and puts it into the device, which we have already stated as before. And we also define the max action. Like now the main networks are to be followed. So one is the actor, one is, you can say, critic, which takes state dimension and action dimension to device, to the set device, and these are the main networks where the training will happen. And now we also have to call the define the or create target networks, which are, you can say, slow moving copies for stability. So we define the actor target as actor. So basically, it's the same code. Let's define it as a target, and this should be also the target. And so, okay. Now we initialize the weights of the target. Initialize target weights match main weights. Exactly. So it's basically we load the parameters from the actor to the target actor, and similarly for the critic also. Now we also define the optimizers. So for the actor, we define the actor optimizer. It's optim.anim self.actor.animators. And the learning rate is the actor learning rate. Then similarly for the critic, and we define the replay buffer now. So it's the size of it will be the memory size which we defined earlier. And we also define the noise as noise, taking that dimension, like action dimension. Now for the select action, now we define a function select action. So this here we define that the state, basically convert the state, tensor, or reshape it by making it kind of like a two-dimensional array, and move it to the device as said before, and return the action selected by the actor to CPU, and convert it, get the data for it, and then convert it into a NumPy array and flatten it. So this outputs a value, and we get an action which the actor outputs. Now we define a train function. So if self.replay buffer size is less than that size, then we return. We don't have to do the training. We don't have enough data to train yet. Then if there's the length of the replay buffer is greater than the batch size, we sample the data for a batch. So we get state, action, reward, next state, and done as self.replay buffer sample. The batch of batch size, as said previously. So now the first thing is we update the critic. For the critic, we compute the target Q value. So we use this target actor. We have to compute the target Q value. So for it, we use the target actor to select the next action because it hasn't moved so. And then we use the target critic to evaluate that next action. So with torch.noGrad, we select the next action, self.actor target, and next state. So we get the Q value for the select the action from the next state, and then target Q. So for all the next states, we will get the next actions. And to get the Q values for that next state and next action. And then we basically use the formula reward plus 1 minus 10 times gamma times target Q. So we get the target Q value. We compute the current Q values also, like the current Q estimate using the normal critic, which is being trained for the current state, and then we also compute the loss current, the critic loss, which is the MSC. So it's basically the critic loss, which is between the target Q value and the current Q value. And then we optimize critic. So set dot critic optimizer dot zero grad, and then move the loss, like get the derivative of the loss, and then perform the step gradient as descent. And then now we have to update the actor. So the actor wants to maximize the critic's estimated Q value. So we pass the current state actor, get an action, and pass that to the critic. We take the negative mean of loss because we want to maximize the value, and loss is basically is minimized. So the loss will be self.critic the Q value for the current state, like the current state Q value with the state, and the next state the actor thinks the agent will be at, and we get the mean of it. Now we optimize the actor in the same way as we optimize the critic. Now is the third thing, which is soft updates. The critic and the actors are being trained over here, but when to update the target network. So we update it slowly, and that process is called soft updates. So slowly update target network parameters. So like the formula is theta target, weights of the target is tau times like the local normal weights of the normal network times the 1 minus tau plus 1 minus tau times the target weights. So it's basically for params and target param in set of like for the actor targets and the actor, local actor and the target actor. We just copy the params of target params as tau times local params plus 1 minus tau times the target param data. Similarly, we update it for the critic. Now we proceed with like this is done. The agent class is implemented. Now we proceed with the training loop and visualization. So first we define the run project, or we can directly move on to making the environment. From the gym, we get the state dimension, which is observation space shape 0th value. Similarly, the action space. And then we get the max action from environment dot action space 0th element, and then we create the TDP agent. We take state dimension as a parameter, then the action dimension as the max action argument. So for the duplicate and array for rewards, like for the rewards tree, we then start a training loop or episode in range, max episodes. We get state, current state of the environment and reset it. Make it reproduce every time we reset it using the seed. And then we reset the noise as well. Use a new episode. And now the episode reward is 0. And now we start let the agent move. So with the max number of steps. So like the action, we select an action from the agent, and then we sample the noise basically. We just add a noise on the action. So this is important. We clip the action from max action to like the negative, like maintain the range of this only, like ensuring the action is valid. It is not out of bounds. So this is basically the first thing is select an action with added noise or exploration. Then we have the second step is make the environment. Let's step into the next state. So next state, reward. Then we'll get the dominated, truncated from environment.step method. And we compute whether the environment is in the done state, is dominated or truncated. Now, third is store the experience. So agent dot push state action reward next state. Then so we train the agent. Now one step of gradient descent is basically so agent dot train. But it checks whether like the deep buffer has reached its maximum batch size or not. Otherwise this will not be performed. Now we get the we have moved to the next state. We update the current state and like get the reward we got from the taking that step. If it is done, we break it and we basically for that loop we add that episode reward to maintain the rewards history. And now let's say if episode +1 or 10 equals to 0, we average the reward as mean rewards and print the episode and the average reward. Let's see how it works. And let's see whether we have done any mistake or not. Yeah. So TTP agent has no attribute action. Okay. It has okay. In which line? So it should be after. Meanwhile it is training, let's move on to the next step, which is basically visualization. So we create a figure first of, like, let's say, define the size as this. We plot the reward history. We keep the title as training, progress, and we set the X label as episode, the Y label as total reward, and we set it to be true, and we show the plot. And yeah, and we can also optionally do this, like rendering the display. This might not work on the collab. Let's see. We get the action, no noise during testing, and then we get the next state, record, it's terminated, truncated, like stepping the test, like stepping the environment to the new next action. Sorry, the next state. We take that action, we update the next state, like the current state to be next state. If it is done, then we break, we close the environment, and we basically print the record. Let's see if how's the training so far. The record is increasing, but let's see where it goes after 200 epochs. Sorry, not the epochs, but the episodes. Yeah, so it's basically converging at 127 or 126 values. Okay, so the training has been done. Like in the end, the reward was not stable. Let's see the plots here. So the training was like this. It was converging till around 126 value. Let's try to render it. Let's see. So the total reward we got is minus 0.06. Okay. The testing also works, and in the testing it performed good as compared to how it was performing in the training. Because we added the noise, now we don't have to add the noise. Yeah. So let's end up with some of the questions we can think of, like why we separate networks, like active or predict, like in simple Q learning. KQN, you can say we just pick the action with the highest Q value, but in continuous space, you can say chain every possible action, which is infinite. Find the max is impossible. And secondly, so we trained a second model, you can say neural network, after specifically to predict the action that maximizes the Q value. The critic just judges it. And now, let's say why the target networks. RL is unstable. Reinforcement learning is unstable because the target changes every time you update the network. So we create target copies of our network. We don't update it with gradient descent. Instead, we perform a soft update. Let me move the target weights by 0.5% so it's closer to the main weight at every step. This makes the target move slowly and smoothly, stabilizing the training. Another is why the noise. So if your policy is deterministic, you will always take the exact same path and never learn anything new. So we add noise. Unlike Gaussian noise, we add volume noise because it is coordinated in time. Like if one person walking, if they step left, they're likely to keep drifting left for a moment. So this creates smoother exploration, which is physically consistent for controlling things like motors, pendulum circles, etc. Thank you. I hope you like this video.